So today we will be reviewing some organic functional groups. So what is physiological chemistry? Physiological chemistry is the chemistry of the organs and tissues of the body and of various physiological processes related to life. Therefore, we will be talking about the synthesis of amino acids, proteins, carbohydrates, fatty acids, and their metabolism, which makes it important for us to spend some time reviewing the basic groups that all these entities are made of, which are called the functional groups. There are about 10 million organic compounds that have been discovered and synthesized. It is an impossible task to learn, understand, and remember the physical and chemical properties of so many compounds. Fortunately, it is not as formidable as you think. While organic compounds can undergo a wide variety of chemical reactions, only certain portions of the structures undergo chemical transformations. These atoms, or group of atoms of an organic molecule that undergo predictable chemical reactions, are called functional groups. These functional groups, in whichever molecule they are a part of, undergo the same type of chemical reaction. Therefore, we do not have to study the chemical reactions of even a fraction of those 10 million compounds. Additionally, these functional groups also serve as a basis for naming the compounds. We need to identify only a few characteristic functional groups and then study the chemical reactions that each of them undergoes. Now, there are about 100 different functional groups. However, within the scope of this particular class, we will be focusing on only about 10 of these functional groups. The first one of which is hydrocarbons. Hydrocarbons, as the name would suggest, are made up of carbons and hydrogen. It is a covalent, non-polar functional group, unlike oxygen and hydrogen, which is covalent and polar. The reason this is non-polar is the electronegativity difference between carbon and hydrogen is only 0.4. Now, these hydrocarbons can be further divided into aliphatics and aromatics. Linear chain hydrocarbons are aliphatic and cyclic hydrocarbons are called aromatic. Now, within the aliphatics, they are further differentiated into three different types. They are alkanes, alkenes, and alkynes. Let's take a look at the first one, which are the alkanes. Alkanes are saturated hydrocarbons that therefore contain only hydrogen and carbon atoms bonded to each other and typically follow the chemical formula CnH2n plus 2. You will notice that there are all single bonds between carbons and hydrogens. The next one are alkenes. These are unsaturated hydrocarbons that contain at least one carbon to carbon double bond and typically follow the chemical formula CnH2n. Alkynes. This category of hydrocarbons are again unsaturated and contain at least one carbon to carbon triple bond and typically follow the formula CnH2n minus 2. And lastly, we have aromatics. Aromatic hydrocarbons are called aromatic compounds because they contain benzene as a part of their structure. They actually have an aroma. So benzene here is a cyclic hydrocarbon with a chemical formula C6H6. Now, how do you name these hydrocarbons? Be it alkanes, alkenes, or alkynes. They follow a certain nomenclature based on the number of carbon atoms. For example, if you have one carbon atom, it's called a methane in case of an alkane. If it's got two carbon atoms, ethane, 3 propane, 4 butane, and so on. Now, this nomenclature actually gets a little more simple after 5 carbons, because then it becomes synonymous with the number of carbon atoms. For example, 5 is pentane, 6 hexane, 7 heptane, 8 octane, and so on. So the first 4 are the ones that really not synonymous. So how do you remember these? You can try using a mnemonic. A mnemonic is nothing but an acronym. So for example, we have 1M, 2E, 3P, and 4B. So you can try remembering the first four with a mnemonic that goes something like Maggie enjoys pacifiers and bottles. Okay, and then the next are all synonymous with the number of carbon atoms. So Maggie enjoys pacifiers and bottles. IUPAC nomenclature for alkanes. Now there are certain rules that you need to follow when naming these compounds. Now the first and the most important rule is you need to identify the longest carbon chain, also called the parent hydrocarbon chain. Rule number 2 is identify the side chains or the substituents. The next rule is to number the substituents to have the lowest number, and we'll see what these rules mean as we go through some examples. Now within the third rule there are some sub rules. Okay, if you have more than one of the same type of side chain, you add the prefix di, tri, and so on. So if you have something like 3-methyl, 5-methyl, it becomes 3,5 dimethyl. Had it been 3-methyl, 5-methyl, 7-methyl, it would have been 3,5,7 trimethyl. Two side chains on the same carbon atom, the number should be written twice. So if you have 3-ethyl, 3-ethyl, it becomes 3,3 diethyl. The next sub rule is if you have different side chains, they should be written in alphabetical order. So if you have 2-methyl, 6-butyl, it becomes 6-butyl because B comes alphabetically first, 2-methyl. Now this is an important one that's easy to be confused with, because even if numerically you have the methyl coming on the second carbon, it's always numbered or labeled alphabetically. And then there are some less important rules which are about punctuation. So you put commas between numbers and you put hyphens between numbers and letters, and there is no space between successive words. Now this slide talks about primary, secondary, tertiary, and quaternary carbons. So within a hydrocarbon compound, you need to identify if the particular carbon is a primary, a secondary, a tertiary, or a quaternary. And the way you do that is you just look at the carbon that's involved and you look how many other carbons it's attached to. So if you were to look at this carbon, it is a primary carbon because it's bound to only one other carbon, which is this one. If you were to look at this particular carbon, it's a secondary carbon because it's bound to one carbon on the left, one carbon on the right. This particular carbon is a tertiary carbon because it's bound to three other carbons, one on the left, one on the right, one on the top. And then you have a quaternary carbon which is bound to four other carbons. So that's what primary, secondary, tertiary, and quaternary carbons are all about. Now let's take a shot at naming some of these compounds. So the first rule is to choose the correct ending. Now within this hydrocarbon, you will notice that they are all single bonds. It is a saturated hydrocarbon, which means it is an alkane. So the first rule is choose the correct ending. So this particular compound is an alkane. It should end with ANE. The next rule is to identify the longest carbon chain. Now the longest carbon chain within this compound would be 1, 2, 3, 4, 5, 6. Well, not really, because if you go in this particular order, 1, 2, 3, 4, 5, 6, 7. Now you have 7 carbons, which is the longest carbon chain that you can have within this particular compound. Okay, so this is your longest carbon chain. Now the third rule is to attach the prefix according to the number of carbons. So this has 7 carbons, so this becomes a heptane. Next, you assign numbers to each carbon. Now these numbers need to be assigned in such a way that you encounter the substituent as early as possible. So now let's go from left to right. So you have 1, 2, 3. Your third carbon has a methyl. 4, 5, 6, 7. Now that's one possibility. The other possibility could be you go 1, 2, 3. Now this particular carbon has two substituents. It has two methyl groups. So whether you go from left to right or you go from right to left, you encounter the substituents on the third carbon. So which is the way that you really need to go? In this case, you need to go from right to left, because your third carbon, as you go from right to left, has higher priority substituents, which means it has, this particular carbon has two carbons, whereas if you go from left to right, your third carbon has only one carbon. So the substituents as you go from right to left have a higher atomic number. If you were to add the atomic number for two carbons, 6 plus 6 is 12. If you add the atomic number for this particular carbon, it's only 6. So this carbon becomes the higher priority carbon, carrying the higher priority substituent. So in this case, you number them from right to left. The next rule is to determine the name for the side chains. Now, your third carbon has a methyl, it has another methyl, and then your fifth carbon has one more methyl. So they are all methyl substituents. Okay, now you attach the name of the branches. So which means that this particular compound is 3-methyl, 3-methyl, 5-methyl heptane. We are not done yet, because we need to group the similar branches, which means that this particular compound becomes 3,3,5 trimethyl heptane. Okay, next let us try naming some alkenes. Now most of the rules for the nomenclature of alkenes remains the same as the nomenclature for alkanes, with a few additions. The first addition is you need to assign the lowest possible number to the carbon-carbon double bond, which means if your alkene has a double bond between the second and third carbon, it becomes a 2-alkene. If it has a double bond between the fourth and the fifth carbon, it becomes a 4-alkene. That's what it means. Indicate the location of the double bond by the location of its first carbon. Then you have multiple double bonds which take the form of diene, triene, and so on. And then there's something new here which says that determine if the carbons adjacent to the double bond are on the same side, cis, or opposite side, trans. Similar to cis and trans, we have another nomenclature which is called E, which is entgegen, which means opposite, and Z, zusammen, which means together. So if they are on the same side, you can label them as cis or Z. If they are on the opposite side, you name them as trans or E. We'll see what that means. Now let's try naming this particular alkene. Now the rule number 1 is to identify the correct ending. Okay. Now this particular compound has one double bond between two carbons, so the correct ending for this particular compound is going to be ENE. Okay, the next rule is to identify the longest carbon chain. So if you go from left to right, you have 1, 2, 3, 4, 5 carbons. So that makes this compound a pentene. The next rule is to specify the location of the double bond, and that the double bond should happen as early as possible. So now if you were to go from right of your screen to the left, your double bond would be on first, second, third, and fourth carbon. So it would be between the third and the fourth carbon. But if you were to go from left to right, it would happen on the first, second, third. So it would happen between the second and third carbon. So in this case, you need to go from left to right and then specify the location of the double bond occurring as earliest as possible. So that would make it a 2-pentene. Okay, then we need to identify if there are any substituents on any of the carbons. So as you go from left to right, you have 1 to the third carbon that has a substituent which is a methyl group. So now in this case, this particular compound becomes 3-methyl 2-pentene. Okay, let's take a look at this one. So the correct ending would be ENE because you have a carbon-carbon double bond. However, let's remember that there are 2 double bonds that makes it a diene. And this is a symmetrical compound. No matter which way you go, left to right or right to left, you have 4 carbons. So that makes it a butadiene. And then you have the carbon-carbon double bond happening on between the first and the second carbon, and then the third and the fourth carbon. It remains the same even if you were to go from right to left. So your double bond would be between the first and second carbon and third and fourth carbon. So that would make this a 1,3-butadiene. Now let's try to determine if the substituents on the double bonds are cis or trans or Z or E. These systems can be used interchangeably. You can use whichever one you are comfortable with. It can be either cis or trans, or it can be Z or E. So in order to determine if they are cis or trans or Z or E, you need to determine the substituents on the double bonded carbons. Next, you need to determine if the substituents based on their priority are on the same side of the double bond or on the opposite side of the double bond. Let's take a look at the compound on the left. So this is again the 3-methyl 2-pentene. Now the substituent on the double bonded carbons, the first carbon, or rather the second carbon, one of the substituents is hydrogen, which is really a low priority substituent. The other substituent is carbon. So carbon, or rather it's a methyl group, but the carbon is bonded to carbon. So the carbon has a higher atomic number as compared to the hydrogen. So that becomes a higher priority substituent. Likewise, on the other carbon, you have one substituent which is a carbon, and then you have another substituent which is a carbon that's then bound to another carbon. So you have two substituents. One is a methyl group, the other one is an ethyl group. So because this has a higher priority, because it has a higher atomic number, you have a carbon bound to another carbon, this becomes a higher priority. Now these two substituents are on the same side of the carbon-carbon double bond, making this particular compound a cis 3-methyl 2-pentene or Z 3-methyl 2-pentene. In the example on the right hand side, you have the higher priority substituents on opposite sides. So that makes this particular compound a trans 3-methyl 2-pentene or E 3-methyl 2-pentene. The next functional group that we'll take a look at are the alcohols, which has the hydroxyl group. Now just like you had the primary, secondary, tertiary, quaternary carbon, you have a primary, secondary, tertiary alcohol, in which case the carbon, for a primary alcohol, the carbon that's bound to the hydroxyl group is bound to one other carbon. For a secondary alcohol, the carbon that's bound to the hydroxyl group is bound to two other carbons. For the tertiary alcohol, the carbon that's bound to the hydroxyl group is bound to three other carbons. You cannot have a quaternary alcohol. So a couple of additional rules here, in addition to all the rules that we talked about for alkanes, are that you assign the lowest possible number to the hydroxyl group. In other words, the hydroxyl group has to come first. And the other rule is you have other substituents preceded by their numbered location come first, followed by the location of the hydroxyl group and the name. Which means if you have, let's say, another substituent which is a methyl or ethyl group, that particular substituent should be numbered and named first, followed by the alcohol. Let's take a look at some examples. Let's take a look at the example that's on the left top. The first rule is to identify the longest carbon chain. So this one has 4 carbons. So that's a bute, and then you need to identify the hydroxyl group in such a manner that you encounter it as early as possible. So if I were to go from right to left, your hydroxyl group would be on the first, second, third carbon. If I were to go from left to right, your hydroxyl group would be on the first, second carbon. So in this case, you need to go from left to right. Now, in addition to that, you also need to determine if there are any other substituents on this particular alcohol. Yes, there is. On the second carbon, you have a methyl group. So this particular compound now becomes 2-methyl 2-butanol. Okay, so it has 4 carbons, so that makes it a bute. Your alcohol is on the second carbon, so that makes it a 2-butanol, and your second carbon also has another substituent, which is a methyl group, that makes it a 2-methyl 2-butanol. Let's take a look at the next one. So this one, the longest chain, is pretty obvious. You have 1, 2, 3, 4, 5, 6 carbons, so that's a hexanol. Okay, if you were to go from left to right, you would have your hydroxyl group on the 6th carbon, which is not really what you want. If you were to go from right to left, your hydroxyl group would be on the 1st carbon, which is what you want. Now that makes the substituents 1, 2, 3 methyl, 4, 5 methyl. So you have 2 methyls on the 3rd and the 5th carbon. So that makes this particular compound a 3, 5 dimethyl 1-hexanol. Let's take a look at this compound on the bottom here. It's a 2-carbon compound. So that makes it eth, and then you have 2 hydroxyl groups. Now just like with alkenes, if you have more than 1 carbon-to-carbon double bond, it becomes a diene or a triene. That's the same case with alcohols. If you have more than 1 hydroxyl group, it becomes a diol or a triol. So this one here is 1, 2 ethane diol. Okay, you have, irrespective of it's a symmetrical compound, irrespective of whether you go from left to right or right to left, your hydroxyl groups are going to be on the 1st and 2nd carbon. So it is a 1, 2 ethane diol. Now the next compound is pretty similar to this one, so you can take a shot at this one. Okay, it's a 3-carbon compound, so it's a propane. You have 3 hydroxyl groups. You have the hydroxyl groups on the 1st, 2nd, and 3rd carbon. So this particular compound is a 1, 2, 3 propane triol. The next functional group that we're going to take a look at are the aldehydes and ketones. Now, one similarity between the aldehydes and ketones is that they have a carbonyl group. They have a carbon that's double bonded to an oxygen. What distinguishes the aldehyde from a ketone is that if there is one hydrogen, that particular functional group becomes an aldehyde. If there is no hydrogen that's bound to the carbonyl, that particular functional group becomes a ketone. The rules again remain the same, just like we had for the alcohol, which is to assign the lowest possible number to the carbonyl group. If it's an aldehyde, it ends with al. If it's a ketone, it ends with one, and then you have the other substituents preceded by the number location come first, followed by the location of the carbonyl group and name. Let's take a look at this one. So the longest carbon chain is 1, 2, 3, 4, 5. And then you have a carbonyl group that also has a hydrogen attached to the carbon. So that makes this one an aldehyde. Okay, it's a 5-carbon aldehyde. So that makes it a pentanal. Okay, one more thing you need to look out for is if there are any other substituents. So if you have to go from your carbonyl group, must be encountered as early as possible. Now, one good thing about aldehydes and ketones is the carbonyl group is always going to be on the 1st carbon. That's just the way, because the carbon is double bonded to, I beg your pardon. So then let's try naming some aldehydes and ketones. Okay, the first compound here has 1, 2, 3, 4, 5 carbons. And then there's a carbonyl group that's bound to another hydrogen. So that makes it an aldehyde. Now one thing about aldehyde is that it is always going to be on the first carbon. Okay, so naming that particular aldehyde group is optional because it's always going to be 1, but if you want to get into a practice of numbering it to be on the safe side, feel free to do so, but you really don't have to number the aldehyde. So now this is a 5 carbon compound. It's an aldehyde, so it's going to end with al. 5 carbons makes it a pentanal. Now wait, there is another substituent. So we have 1, 2, 3, 4. We have a methyl group on the 4th carbon, which makes this a 4-methyl pentanal. Let's take a look at this one. So this is a 1, 2, 3, 4, 5, 6, 7, 8. This is again an aldehyde because you have a carbonyl group that's bound to another hydrogen. Okay, so with 8 carbons that makes it an octanal, and then we have to figure out the substituents. So you have 1, 2, 3, 4. We have an ethyl group on the 4th carbon, a methyl group on the 5th carbon. So this is going to be 4-ethyl 5-methyl octanal. Okay, you always want to have the ethyl first, not because it's occurring first, but because it's alphabetically preceding the methyl. Okay, now let's take a look at the ketones. So this is a ketone because there's a carbonyl group and then you have substituents on either side. The carbon is not bonded to another hydrogen, but it's bonded to some other substituents. That makes this a ketone. So we have 1, 2, 3, 4, 5, 6. We have 6 carbons on this particular compound. Okay, so that makes it and this is a ketone, so that makes it a hexanon. Now we have to look out for the substituents. So we have 1, 2, 3, 4, 5. We have a methyl group on the 5th carbon, and then we have a hydroxy group on the 6th carbon, and then the ketone group is on the 2nd carbon. So this is a 2-hexanon, and now we just add the substituents. So this is a 6-hydroxy 5-methyl 2-hexanon. Again, the hydroxy comes first because it alphabetically precedes the methyl. So 6-hydroxy 5-methyl hexanon. Let's take a look at this one. You have 1, 2, 3, 4, 5, 6, 7, 8. So this is an 8 carbon compound, octa, and there's obviously a carbonyl group that's bound to some substituents on either side. But wait, there are 2 carbonyl groups. So just like with alkenes where it becomes diene, triene, that's the same thing with ketones. Now this becomes, it's not a one, it's a dione. It's a octadione. And we need to figure out the locations of the carbonyl groups. So again, this is more or less a symmetrical compound. No matter whether you go right to left or left to right, you're going to have one carbonyl group on the 2nd carbon, and then you're going to have the other carbonyl group on the 3rd, 4th, 5th, 6th, 7th carbon. That applies even if you were to go from right to left. 2nd carbon, 3rd, 4th, 5th, 6th, 7th carbon. So this is a 2, 7 octadione. Alright, so now the next functional groups that we'll take a look at are acids and acid anhydrides. So acids have a carbonyl group, the carbon of which is also attached to a hydroxy group. So an acid is represented by COOH. And then you have an acid anhydride. An acid anhydride is formed through the process of dehydration of an acid. So you have two acid molecules coming together, losing a water to form acid anhydride. Okay, this is the functional group for the acid anhydride. You have two carbonyl groups that are joined together by an oxygen. Okay, so now let's try naming some of these molecules. So the first one, is it an acid or acid anhydride? Well, it's obviously an acid. You have the carbonyl group, the carbon of which is attached to the hydroxyl group. So you have the longest carbon chain, which is 1, 2, 3, 4 carbons. So that's bute. So it's an acid, so it's butanoic acid. Okay, let's take a look at the next one. We have 1, 2, 3, 4, 5, 6. So this is a 6 carbon acid. Again, acids, just like aldehydes, do not need to be numbered because the COOH is always going to be on the first carbon. Okay, so this is a 6 carbon acid, so that's a hexanoic acid. But wait, on the fifth carbon, 1, 2, 3, 4, 5, the fifth carbon is carrying a substituent which is a methyl group. So this particular compound is 5-methyl hexanoic acid. Let's take a look at this one. You have, this is clearly an acid anhydride. You have two carbonyl groups which are joined together by an oxygen. So what do you have on either side of the functional group? You have 1, 2, 3. You have a 3 carbon acid that's lost a water molecule after coming in contact with its own molecule. This is another 3 carbon acid. So these are propanoic acids. So you have two propanoic acids come together to lose a water molecule and form propanoic anhydride. Now since this is a symmetrical anhydride, you don't really need to name the two propane molecules separately. So this is simply propanoic anhydride. The last one here. So you have, this is again an acid anhydride, two carbonyl groups joined together by an oxygen. On the left side, you have a 2 carbon acid, which is an ethanoic acid. On the right hand side, you have a 3 carbon acid, which is a propanoic acid. So you have ethanoic, propanoic, anhydride. Why do you name ethanoic first? Because alphabetically it precedes propanoic. Esters. Esters are molecules that are formed when you have a carboxylic acid reacting with an alcohol to lose a water molecule. So you have an ester that has a carbonyl group, that's the carbon of which is joined to an oxygen with substituents on either side. So that's an ester, a carbonyl group, the carbon of which is joined to an oxygen. So how do you name esters? The name of the alcohol radical comes first, followed by the name of the acid. Since you only have acids and alcohols coming together to form esters, you always name the alcohol radical first, followed by the acid. Again, the alcohol radical uses YL as a suffix, and the acid uses O8 as a suffix, which means at the end of the name. So let's see an example. Here you have ethanoic acid reacting with ethanol to lose a water molecule and form this ester. Again, remember the carbonyl group, the carbon of which is joined to an oxygen, is an ester. So how do you name this ester? So you have the alcohol radical, which is the ethanol, so that's going to come first, except for you're going to change it, the suffix, to YL. So this is going to be ethyl, and then you use O8 for the acid. So this is going to be ethyl ethanoate. Let's try naming this one. So you have 1, 2, 3, 4, 5. So you have a 5 carbon acid. again, how do you figure out which of this molecule is the acid, which one is part of the alcohol? The acid is always going to have the carbonyl group, the carbon double bonded to oxygen. So on the left you have what is coming from the acid, on the right you have what is coming from the alcohol, which is methanol. It's a one carbon alcohol. So this particular molecule is methyl pentanoate. Now sometimes you can have cyclic esters, which are formed by the intramolecular esterification of hydroxycarboxylic acids, which means these are acid molecules that not only have the COOH group, the carboxylic acid group, they also have a hydroxy group. They have the OH group. So just like you saw in the last slide, you have the carboxylic acid, you have the alcohol, all of that is on the same molecule. So this molecule can undergo self-esterification. You can have the acid group reacting with the hydroxy group to lose a water molecule. This is called self-esterification. The carboxylic acid and the hydroxyl group react intramolecularly and to form a cyclic ester. Now the cyclic esters can be named in a very specific manner. There are two determinants for naming lactones. Cyclic esters are also called as lactones. So they are named depending on the number of carbons in the acid. If you have 2 carbons, it's aceto, 3 carbons, propio, 4 carbons, butero, 5 carbons, valero, and so on. And the naming also depends on the number of rings in the ester molecules. So if you have 3 rings, it's alpha, 4 rings, beta, 5 rings, gamma, 6 rings, delta. Let's take a look at an example. So here you have an acid. It's a hydroxycarboxylic acid. Not only you have the COOH group, you also have a hydroxy group on this molecule. So now this molecule, because of the presence of hydroxy group and the presence of the carboxylic acid group, can undergo self-esterification. So even before we try to name the ester, let's try to name this particular acid. So the longest carbon chain is 1, 2, 3, 4, 5. So this is clearly pentanoic acid. However, you also have a substituent on the 5th carbon, which is hydroxy group. So this is 5-hydroxy pentanoic acid. Now, in this molecule, now you have, if you arrange this molecule in this particular manner, you have the hydroxy group of the acid coming in contact with the hydroxy group of the alcohol to lose a water molecule and to form this cyclic ester. Now remember, the naming of the cyclic ester depends on the number of carbons and the number of rings in the molecule. So let's count the number of rings. So this one has 1, 2, 3, 4, 5, 6 rings. So this is a delta. Okay, let's count the number of carbons. So this has 1, 2, 3, 4, 5 carbons. So this is a valero. So this is a delta valerolactone. Remember, cyclic esters are also known as lactones. Now the next functional group are called amines. Now if you were to simply consider ammonia, which is NH3, where one of the hydrogens is replaced by a substituent, you would have a primary amine. If you consider the ammonia, where you have 2 of the hydrogens being replaced by substituents, you have a secondary amine. If you have ammonia where all of the 3 hydrogens are getting replaced by substituents, you have a tertiary amine. Okay, couple of additional rules in the naming of amines is the chain is numbered to locate the amine group and substituents. And each alkyl group bonded to the nitrogen atom is named as a N-alkyl group. What does this mean? We'll see in a minute. So, for example, this is an amine. You have NH2 where one of the hydrogens is replaced by this particular substituent. It's a 3-carbon substituent. So this is 3 carbons is propa, and this is an amine, so this is propanamine. Now this is where the first rule comes into picture. The chain is numbered to locate the amine group. So irrespective of whether you go from left to right, right to left, your amine group is located on the second carbon. That makes this a 2-propanamine. Let's try naming the next one. So the longest carbon chain is 4 carbons. So this is a butanamine. Now we have to also figure out which carbon the amine group is located on. So going from right to left would make it the 3rd carbon. Going from left to right would make it the 2nd carbon. So the 2nd carbon it is. So this is 2-butanamine. Now however, just hold on for a second, the amine group itself is also carrying a substituent, which is a methyl group. This is where the second rule comes into picture. Each alkyl group bonded to the nitrogen atom is named as N-alkyl. So this is N-methyl 2-butanamine. Okay, N-methyl because the methyl group is located on the amine group, and 2-butanamine because it's the 2nd carbon that's carrying the amine group. Now similarly, let's try naming the next one. So this is a 2-carbon amine. Okay, so this is a ethanamine. Okay, the amine group is located on the 1st carbon, so you may choose to number it or not number it. It can be optional. So this is a ethanamine. Now however, the amine group itself is carrying 2 substituents, both of which are methyls. So this is N-methyl ethanamine, or you can also write this as N-dimethyl ethanamine. The last functional group that we are going to take a look at are the amides. Now the amides are derived from carboxylic acids and are therefore also called as acid amides. Now if you were to simply take a look at the carboxylic acid group, and if you were to replace the hydroxy group by an amine group, what you get is an amide. So an amides have the carbonyl group, the carbon of which is also bound to an amine group. So make sure you can distinguish between amines and amides, which are more commonly confused. The amides has the amine group where the carbon is also bound to double bonded to an oxygen. Okay, so now let's try naming this particular amide. The longest carbon chain is 3 carbons. So this is a propanamide. Now however, the amide group is also carrying some substituents. The nitrogen is carrying 2 substituents, both of which are methyl groups. So this is a N, N dimethyl propanamide. Okay, that's how. So naming them is very similar to naming amines, except for you have to bear in mind that the amide group has a carbonyl, the carbon of which is bound to an amine group. Now what I want you to take a look at is one of the most important amides. Now this particular structure is a cyclic 4-membered amide, also known as a beta-lactam. Now why do you need to care about beta-lactams? Because beta-lactams form the core structure of antibiotics, the most important one being penicillin. And that's the structure of these amides is the logic behind the functioning of antibiotics. Now, the way antibiotics really work is they disrupt the cell wall synthesis of bacteria. And the reason these amides can disrupt the cell wall synthesis of bacteria is the way you're looking at the structure, it's arranged in squares, and this particular structure is under tremendous stress. Okay, so this particular bond, the carbon that's bound to the nitrogen here, that particular bond is under tremendous stress, and it's looking to break free, and it's looking to stabilize itself. And the way it breaks free and stabilizes itself is it breaks off this bond and it stabilizes itself by binding to penicillin binding proteins. These penicillin binding proteins are the enzymes that are involved in bacterial cell wall synthesis. So by breaking off this bond and bonding to the penicillin binding proteins, it does two things. One, it stabilizes the structure of the beta lactam, and more importantly, secondly, it neutralizes the enzyme that's involved in cell wall synthesis. So now that particular enzyme can no longer function because it's bound to this, that enzyme is bound to this carbon. So it can no longer function and play its role in the bacterial cell wall synthesis, and that's how beta lactams inhibit bacterial cell wall synthesis.